Hi everyone! In this video I'm going to be showing you how to use the dot product to be able to solve for the angle between two vectors. So we saw earlier that we have this awesome formula for the dot product where it's the magnitude of your two vectors multiplied together and then multiplied with the cosine of the angle. So we can use this formula, use this relationship, as long as we know the dot product and the two magnitudes, we can work backwards and then solve for theta. So I wanted to show you an example in 2 dimensions, and then we'll extend this to 3 dimensions. So first off, we want to kind of outline some steps for ourselves. So maybe step 1 can be solve for the dot product. Step 2, we can then solve for the magnitudes of each vector. So that's its length. And then our third step can then be solving for theta, solving for the angle. So our first step, solving for the dot product, we can do this algebraically. So essentially we're looking at the x components of each vector, the y components. So we're multiplying similar components and then adding them together. So our first step here, we'll take the x's, so 8 times negative 9, and then I'll add 5 plus 2. Computing that, I get negative 72 plus 10. And then by adding, I get negative 72. We want to make sure that we're using proper notation here, so using the vector symbol above, and then using the dot to show that I did the dot product, because there are actually multiple ways of multiplying our vectors, right? We can't just say times. So now that this side is sorted out, our next step is going to be let's actually find the length or the magnitude of each vector. So our formula for the magnitude kind of comes from the Pythagorean theorem, right? We can think of each vector as a right triangle. We can square its x components, square the y, and then take the root of that. So for my magnitude of vector A, I'm going to go 8 squared plus 5 squared, work within my square root, and just to keep things tidy, to keep things exact values, I'm going to leave my answer as root 89. I'm going to repeat this process for vector B, so going negative 9 squared plus 2 squared, and then working through till I get 85. So once we've got all these kind of 3 pieces done, we've figured out numbers for most of our formula. Our next step here is going to be just taking everything we found and subbing it into our equation. So I'm going to be using the formula A dot B equals magnitude of A multiplied by the magnitude of B times the cosine of theta. So I know for our dot product we found negative 62, so we'll put that in. The magnitude of A was root 89, and the magnitude of B was root 85. So we know those 3 things. We're going to be solving for theta. So in order to solve this, I'm trying to isolate for theta. I'm trying to get theta by itself. I can divide out my 2 radicals. And then my next step in solving is getting rid of that cosine. So I'll do cos inverse. And then throwing that all into my calculator, I end up with 135 degrees for theta. And that actually sounds pretty accurate for what we have in this diagram, right? It's definitely bigger than 90, less than 180. So 135 sounds pretty good. Okay, so that was a nice, easy example in 2 dimensions. We can kind of extend this for 3 dimensions as well. And then I also wanted to show you the same formula, but we've isolated for cos theta, right? So I've taken the same formula and I've just divided out the 2 magnitudes, and that way cos theta is together all on one side. So for this next example in 3 dimensions, we're going to sketch out our vectors again. So I'm using A as the vector 4, 1, 0. So it's traveled 4 along the x-axis, 1 unit along my y-axis, and it hasn't gone up or down because its z is 0. And then for vector B, from the origin, it's gone 1 unit on the x-axis, 3 units on my y, and then down 2. Drawing vectors in 3 dimensions is a little bit tougher. It's kind of hard for us to see, but it's always good to kind of walk, imagine these as steps. 1 step along X, 3 steps along Y, and then 2 steps or 2 floors down. I wanted to show this example kind of using the rearranged formula. We're still going to be solving for the same stuff, so we still need to find our dot product and our magnitudes before we can solve for theta. So our dot product, same process, we're multiplying the x's together, so 4 times 1, multiplying the y's together, 1 times 3, and then multiplying our z's together, so that's 0 times 2. And then as we add things up, multiply and add, we end up with a dot product of 7. So it wasn't too bad. The only difference with 3 dimensions is now that we also have that z that we had to worry about. When we're finding our magnitudes now in 3 dimensions, we actually get to use the same process. So we're going to take our x squared plus y squared plus z squared, throw that all under the root. So for my magnitude of a, I've got 4 squared plus 1 squared plus 0 squared. And then again, I'm leaving this as exact values just to keep things clean. So for my magnitude of a, its length, we get root 17. We'll repeat the whole thing for the magnitude of vector b. I need to figure out what the magnitude of both vectors is in order for me to be able to solve. So after doing that, I've found that my magnitude of b is 14. Alrighty, so we found each part. Now it's just a matter of kind of filling in our formula. The advantage of using this version of the formula is that all of your unknowns, so in this case theta, are on the left, and then everything we do know is on the right-hand side. So we figured out our dot product, that was just 7. We figured out the magnitude of a, which was root 17, and the magnitude of b was root 14. And then this is a little bit nicer because the only thing we have to do now is take the cos inverse. We don't have to worry about dividing. And then throw everything into your calculator, make sure you're in degrees. We end up with 83. So this diagram, it's a little harder to see because we're trying to represent things in 3 dimensions. So it might not look to scale, especially since we saw the magnitude of a was larger. But I think 83 sounds like a pretty good angle, right? If I know vector a is coming out this way to the left and b is kind of coming down, 83 sounds pretty good for that. So it's easy for us to, visualize our vectors in 2 and 3 dimensions. But the dot product and being able to solve for the angle between 2 vectors, it isn't just limited to 2 and 3 dimensions. You can actually extend this to, vectors with 5 components or even 10 or 20 components. It's just a matter of solving for the same 3 things, finding your dot product and the magnitude of each vector. If you are doing this with vectors with 20 components, it just means your dot product is going to have 20 pairs of numbers, and your magnitudes are also going to have 20 pairs of numbers. But it's really awesome that we're able to use this and extend this. So I hope you enjoyed this video, and I really hope it helps. Good luck!